Hi. So last lecture we were discussing about deterministic IFS, and we learned how to find out these parameters R as theta, phi, E and F, which correspond to reflection, scalings, rotation and translation, both in horizontal as well as vertical direction. And and we discussed some examples also. We started with Sierpinski's gasket, and then we also saw that initial object can be taken anything. It doesn't really matter that you start with the gasket and you end up with the gasket, or you start with some other object, you end up with the same object. Once the rules are defined, then whatever object you start with, you will end up with the final product, which will be the attractor of that particular IFS. So that's what we did last time. I'll just recap that with what we did last time. And one of the examples, I think I gave you this one, where we had this little fractal there, and then we saw, and by the side of it, you see on the right side the R as theta, phi, and E, F values which correspond to this particular fractal. Now we saw that you see each of them is doing this half and half. The R and S values are half and half, so whole fractal is reduced by half of its size. Then first I'll just discuss the translational values are 0 and 0.5 in the vertical direction for the blue one. For the red one it is 1 and 0.5, and for the green one it is 0.5 and 0.5. Now here in this example we have some standard rotations also. So for the blue one it is minus 90 in the extra for the horizontal lines and minus 90 for the vertical lines. And remember, the counterclockwise direction is always taken as positive. And similarly for the red part, for this half part, it's 180 degree and 180 degree both counterclockwise direction, both for horizontal as well as vertical line. That means the whole body is being rotated this way. So now these are some standard things. It's easily identifiable. The 90, 45, these angles you can easily identify, and there is no problem with that. But sometimes what happens, these angles may not be straightforward. So when these pieces are not, maybe the scaling is not half, maybe it is 0.29, who knows. So when the pieces are not scaled by the obvious amounts like half or 1 by 4, 1 by 3, 2 by 3, which can be easily identifiable, but if scalings and rotations are not standard scalings and rotations, then we have to measure it physically, the distances as well as angles. So you can have generalized fractals. Like this is one of the examples. You have this example, this black picture, and easily you can see this consists of 3 parts. But you see here this part is scaled by a different amount as compared to this part. This part is a bit smaller than these parts. So you see, if I divide them in three parts, the red one, the violet one, and the green one. So there are these parts, but green one is a little bit smaller than the other parts, and it is also rotated slightly, and the rotation is not standard rotation. It's not 45 degrees or it's not 90 degrees. It's somewhere around 10-12 degrees. We do not know. So we actually have to measure it. So it is convenient to specify again the point as the origin of the coordinate system. So where we can take the lower left corner as the origin of the coordinate system. But in general, you can use use any symmetry available. You can use it origin here also. It doesn't really matter. The rules will be changed accordingly. So first of all, the usual procedure is, first of all you find the scalings, and if any reflections are involved, then you find the reflections. So first of all you find the R and S values. Then we find theta and phi values, that means the rotational values for horizontal and the vertical lines. And thirdly, in the end, we will find what values of the translations are there. So by how much distance these different parts are moved in horizontal or in vertical direction. So that's what we have to find out. And here is a little bit IFS table which generated this fractal, and you see by using a scale you can find out you can find the shifting of the red part. First of all, the blue part is very straightforward. 0.5, 0.5. So actually you scaled it half and half. No rotation. So the r, theta and phi values are 0 and 0. And there is a translation in horizontal direction by half of the amount, half of the total unit length. So this is a straightforward thing. Now for green one, well, before that, let us discuss the red one. Red one is again, the scaling is half and half. There is no rotation, but the shifting is not standard shifting. In the x direction, it's a quarter of a distance, so 0.25, that is standard. But in the y direction, it is shifted by 0.433. So this shifting we have to measure, this shifting we have to measure, and all these shiftings for the violet one, for the red one, and for the green one, these shiftings are to be noted. And green ones, you see I was discussing that the angle seemed to me about 10 to 12 degrees, so it is indeed 10 degrees. So the actual angle by which this point is rotated, this will be 10 degrees, and the scaling is 0.4 and 0.4 as compared to half for the violet and the red part. The green part is a little bit more squeezed or a little bit more contracted, and there is no translation in x direction or in y direction. So that's the final IFS table for this deterministic fractal. It looks like this. And again, if you take any starting object, ultimately the whole picture will converge to this particular fractal if you are using these transformations. So now as in one of the earlier lectures we saw the picture of a tree, and I told you that I will be giving you the IFS rules, the deterministic IFS rules, to produce this beautiful picture of a tree. It's a very complicated tree, but yes, you can create this tree using some very simple IFS rules. So it's very easy to see that these branches, this picture of the tree, you can break it in 4 different parts. First of all, these 4 parts, which are exactly the replica of the original tree, but rotated by different amounts and scaled by different amounts, right? So this it is very easy to see the 4 main branches of the tree, which are scaled copies of the whole trees. These pieces in this picture have been pulled apart slightly to emphasize this decomposition, that yes, this branch, this branch, this branch, and this branch are indeed a copy of the whole tree. Then the trunk, the thing is how to produce the trunk using this tree. I have to produce this picture, this trunk. Like if you leave this 4 part, the trunk is not there. So for using this picture, there is a bit of common sense or a bit of trick is involved. You simply shrink the tree too much in horizontal direction. You just squeeze the tree in horizontal direction. So that is this part of lollipop kind of looking thing, what you see here, a small ice cream. You have a stick and the lollipop on top of that. So this is a squeezed part horizontally. This tree has been squeezed with a large amount, and then same trick has been used, and this has been inverted, squeezed as well as rotated in the opposite direction. So and when you combine these two, then you get a trunk. So this simply shrinking the tree a lot horizontally works for the top of the trunk, but makes the bottom of the trunk also too thin. So to compensate for that, I will have to use 2 shrunken copies of the tree to make the whole trunk. So that's what it is, and I'll give you the rules for that. In fact, I would like you to produce your own trees, creating your simple programs for IFS. That's what your task should be. So these are the IFS rules for this particular tree, but you change the rules a little bit, you will have a different design of tree. So I would like all of you to experiment with that using these rules. What kind of different shapes of the trees can be created, and how the nature creates different shapes of trees probably using deterministic IFS, who knows. So these are the IFS rules, all color coded. Pink for highly shrunken. You see the R value here, 0.05. So it's highly shrunk or highly contracted in the X direction. Whereas in the vertical direction, it's not squeezed much. It is 0.6. No rotation, no translation. This is the pink part. For green part, it is inverted. It is inverted in the opposite direction and then translated in the vertical direction downwards. And then upwards, because when you invert it, it will go down. So you have to bring the whole thing up to make it look like a trunk. Then the blue one is this. These are straightforward. Only thing, different rotations are involved. Otherwise, they're almost and to make it look like realistic, we have used different scaling factors for different colors, so that it does not look like a very similar looking tree. If you reduce those, then it will look like a realistic looking tree, because these rotational factor, the translation factor, and the scaling factors are different for all four different parts. So that's how you make up a tree, and I would like that you should also try to understand this. See, if you don't use this green one, this is an example. If you don't use this green one, the inverted lollipop, then this will be the picture of the tree. If you leave out the second part of the trunk, the lower part, then this will be a tree, and of course it will not be a complete tree. Pretty weak tree, very easy to fall. So it's to make it realistic, you have to use this particular trick also, where this green portion is coded. Okay, so that's about this thing. Now I'll also discuss a few things again okay, before going to that, just a little bit, because today is the Teachers' Day, and I would like you to know a little bit about education. What is education? Then before going further, what is education? What you learn, is that education? What you study, is that education? No. As Einstein said, that education is what remains after one has forgotten what one has learned in school. So whatever you have learned here, once you forget that, whatever you are mugged up or what you crammed up in your school, when you forgot that, and after that, whatever remains in your memory, that is your education. So with that thought, we go further, and we will discuss a little bit. I thought today I wanted to devote a little time to discuss. Because a lot of people, when I give them assignments, they say, oh, this thing looks like a fractal, this thing looks like a fractal, this thing doesn't look like a fractal. So I would like to discuss common mistakes in finding fractals, things that look like fractals but are really not fractals. A lot of people say, oh, if it is symmetric, it is fractal. That is a very common misconception I observed with my students. So first of all, you recall that no physical fractal can exhibit scaling over infinitely many levels. So sometimes you observe a cauliflower and you break a little piece of that, very little tiny piece, and you say, oh sir, this is not going to be fractal again. So yes, the physical fractals do not exhibit scaling over infinite levels. It will only go to 3 or 4 levels, not much. But it's also the reverse is also, you have to take care in mind, that to make a plausible claim of fractality, a pattern must be repeated at least a few levels. It's not that if it is repeated once, you say, oh, this is a fractal. That is also not true. So one of the very famous, well, I do not know whether famous or not, but we found that in literature, the famous painter Dali, his painting, which is titled as Visage of War, that is a depiction of skulls within skulls, and in fact he made this picture during the Spanish War. So we'll discuss that. First of all, let's read it out and see what this painting is all about. This is Dali's Visage of War. It was painted in 1940, and you see the eyes and mouth of this skull contains again a skull here, which has eyes and a mouth. This also has an eye and a mouth. This also has eyes and a mouth, and each eyes and mouth again have same skulls. So we have one bigger piece, then 3 smaller pieces, and then 9 another 9 at another level, and probably if you can imagine, there are probably then 27 more at another level. So this piece of Dali's painting does look like a fractal. At least 3-4 levels, it depicts the fractal nature of the skulls within skulls. So it's eyes and mouth each contain a face, whose eyes and mouth each contain a face, and many of whose eyes and mouth each contain a face. So it's an obvious example of fractals in art. So yeah, I was right. The Dali thought of the Spanish Civil War in 1940 a source of frightening images to him. So he was very much influenced by the Spanish War, and he described, in fact, his contemporary Descartes described the painting as having these eyes are filled with infinite depth. That's what this is, which probably referred to the recursive effect set in motion by self-similarity of these skulls. And in fact, Dali had very profound impact of this painting in his life, because you see, usually painters write their names on the right bottom corner of any painting, but in this painting, this particular painting, Dali has put his own hand print. So it's the handprint in the lower right of the painting. This is Dali's handprint, and this is the only painting by Dali which is signed with his handprint, which probably is a testimony to the power this painting had for Dali. And that's what maybe that is why we are discussing it today, due to that particular power. Okay, let's come back to the common mistakes in making fractals. As I told you, you have to go at least a few levels. So if you just say 2 fists, yeah, there are 2 fists. 2 fists are there, and there is a object, gap, and object. But this does not make a Cantor set. Doesn't mean if Cantor set has a line and a gap and a line that and repeated over that. So if somebody says, oh, this is also a gap and object, that does not make the 2 fists does not continue to even one more level. So it is not a sort of a Cantor set. So and the fists are not split into smaller pieces. The main fractal to claim that something is fractal, we have to see splitting into smaller pieces. The more levels of the pattern, the more convincing the fractality of the picture. Similarly here, yeah, that's it's a example based on Sierpinski's tetrahedron. It's a 3-dimensional Sierpinski's gasket sort of thing. So if you look at this thing, there are 4 pyramids, 3 pyramids on the bottom, 1 on the top, and the whole thing also looks like a pyramid. So there are 2 levels. You may say, yeah, it may look like, but it's only 2 levels. So it is a shape made of 4 tetrahedrons, but the individual tetrahedron do not have any substructure. In fact, in a fractal picture, each part of the picture should have a substructure within that particular part. Now this, if you extend it further, this may look like a fractal. This is more believably a fractal. Same thing, these tetrahedrons are made up of by paper, in fact by high school students in some US college who are studying a fractal course. So this structure has 4 levels of substructure. 1 level, then within that you have another level, then within that you have another level, and within that you have another level. So at least 4 levels of substructure are shown in this particular picture. So this I can say, yeah, this looks like a fractal. Now second thing, if you just have a repeating pattern like a sort of a brick wall, so it's also not sufficient to guarantee fractality. Repetition does not mean fractality. Scaling under magnification means fractality. That's the key point you should remember. If you scale under magnification, that makes something as fractal. So a checkerboard, a chessboard, or a brick wall do have a repeating pattern, but this repetition is just a translational symmetry. It's not fractality, it's translational symmetry. Whereas for fractals, the appropriate transformation is magnification. If you magnify the thing and things still remain same, then it is a fractal. Again, there also you need to be a little bit careful, cautious. Repeating a pattern under magnification alone is also not sufficient to guarantee fractality. In fact, you should have a substructure, not only repetition, just a substructure should be there. And suppose a large piece, then more small pieces, even more smaller pieces, even more smaller pieces. So that's make it a fractal. So for this example, a spiral example, it goes and it repeats and everywhere it looks same, but a spiral is symmetric under magnification about the center point, but about no other point. A fractal it will be symmetric under magnification with respect to any point. Anywhere you look, it should look like same. It's not only with respect to one point. This spiral is a sort of it is a symmetric under magnification, but only with respect to one single point. So if you keep on iterating this process, the limiting shape with just a single point, it will not be a fractal image. Similarly, interesting thing is the Japanese dolls. People say Japanese dolls or Chinese dolls or Russian dolls. In a lot of countries, they make these dolls. A bigger doll, within that a smaller doll, within that is much smaller doll, within that a much smaller doll, and so on. And sometimes you guys prank your friends on their birthdays, like you send them a very huge box, and when this guy opens this box, he gets another small box, then another small box, and another small box, and probably in the end he will get some stupid note saying happy birthday or something. That is not an example of a fractal. So nested dolls are another example of non-fractal involving a single scaling transformation. So a dolls within dolls, or a box within a box and within a box, it's not an example of a fractal. Similarly, there is a advertisement of a French wine, probably. It's called a Deterministic wine, and it's a cat bottle. This is the advertisement of that particular wine. It has a bottle with a cat, and on the bottle itself there is a cat and the bottle. Like the same logo is printed on this bottle. So that means within that bottle there is another bottle on the logo. So within that there will be another smaller logo and so on. But again, it will just converge to a single point, not any other point. By contrast, so basically inside the largest doll nestles a smaller doll, still smaller doll, even smaller doll, and so on. So limit of this process is a single point, not a fractal. Similarly, this bottle label includes a cat and a bottle, with a label that includes a cat and a bottle, with a label that includes a cat and a bottle, and so on. But again, in the limit, this process will lead to a single point, not a fractal. Now, on the other hand, this is another advertisement of cheese, of French cheese. And you see this cow picture. This cow is a laughing cow from whose milk the cheese has been made and being sold in the market. You see this is a laughing cow, and it is wearing 2 earrings. On each earring, the same picture is printed. So that means one cow. On earrings, there are 2 cows at this scale. Now, if you go to the further smaller scale, there will be each cow will have 2 earrings. So 1, 2, 3, 4 cows. Then another scale you will have 8 cows and so on. So now you see the fractality is being shown in this particular picture. 1 bigger object, 2 smaller one, 4 a further smaller one, 8 even more smaller one, and this picture is not limiting to a point. If you go to this point, this will maybe 1 point, but then there is another point here. So where the object will be repeating itself. So if you look at the close-up of this earring, you have another same picture which has again 2 earrings. So same picture. So if both earrings have picture of the cow with 2 earrings, both of which have pictures of the cow with 2 earrings, both of which have pictures of the cow with 2 earrings and so on. So that this limit of the cow picture is a Cantor set. Now that makes a Cantor set a gap and then 2 objects. Within those 2 objects you have another gap and 2 objects. Within that you have gap and another 2 objects. So this is a sort of a Cantor set. It is equivalent to a Cantor set. So those are some common mistakes people make when they study fractals, or when they need to identify fractals. Then it is very common to make these mistakes, and you need to be careful in identifying. Now I would like to stop today here, and in the next class what I plan to discuss in the next class, it will be the random IFS algorithm, which is another way to render IFS images, like we already discussed deterministic IFS algorithm. So before that we will be discussing some standard things, what is the randomness means, what is a chaos game, and all that. So we will do that in the next class, and we will be discussing chaos game in the next class. And then we'll also discuss what is meant by randomness, and how a chaos game is being played, what is the true meaning of randomness, and later on in the course we will also say or discuss that how random IFS and the deterministic IFS do produce same fractal pictures. Thanks a lot.